hypervisor. But before getting into the details about the talk, let me tell you a quick story about how myself and Samuel met for the first time. So in the first 5 minutes, we actually started talking about the difference between a hypervisor and a VMM. And
she did not know about the difference.
No. So obviously he didn't know what is the difference, and I let him choose the title for the presentation. So that's why today the first slide is actually this one, and I'm going to explain why we are actually going to build a container-specific VMM and not hypervisor.
So who knows what a VMM is? Who knows what an hypervisor is? I won.
He did say that he will win this fight. So let's talk a bit about the Linux virtualization stack. We have the host, we have the Linux kernel, and in the Linux kernel, we have KVM. And what we are doing here is that on top of KVM, or using KVM, which in this context becomes the hypervisor, so on top of it, we are running virtual machine monitors, so VMMs. And in this model, each virtual machine monitor is actually going to run one virtual machine. And now that we know what is the difference, I will just let Samuel go back to presenting about containers.
So this slide, for example, used to be container hypervisor. Yeah, I must obey. All right, so we're going to talk about virtual machines, VMMs, hypervisor, and containers at the same time. So it's kind of weird. Containers are not virtual machine, but we're going to talk about container-specific VMMs or hypervisors. So one may wonder, what is this all about, right? What is this all about is that we want to add hardware virtualization as yet another container isolation layer. So typically, when you run your container workload, you want to, by definition, contain it. And the way you do this is by adding all sort of isolation layer around it. Namespaces, SEPCOM rules if you want, C groups. There's a bunch of different technologies. Most of them are actually kernel APIs, software-based technology, that allows you to contain and isolate the workload from the host and from other workloads. So here I'm just giving an example of 3 different layers, but you can add more or less depending on the kind of isolation layer you want to build with your container infrastructure. The one that we are adding here is the hardware virtualization one. So we want to add another new isolation layer around containers, and this time it's hardware-based and no longer software-based. So adding hardware virtualization and lightweight virtual machine as another container isolation layer follows the container security architecture, which is mostly based on defense in depth. So the more secure you want, the more isolation layers you add. And what we're doing is adding a new one based on hardware. So what we're effectively doing is making containers as secure as virtual machine. And I just want to make sure people understand, I'm not saying we're making containers secure. I'm saying we're making them as secure as virtual machines. It means what it means. So the same level of security you have with virtual machine, we want to make it with containers. It could be very secure or depending on what you're looking for. So the way we're talking about this, adding hardware virtualization as a container isolation layer may seem like this is something we're currently working on or it's a work in progress, but it isn't. We've been working already with the community for a long time to make sure that the container ecosystem actually integrates hardware virtualization and virtual machine seamlessly. So there are many ways you can do this, and we worked on many levels of the container software ecosystem. So you can do that from the container runtime interface from Kubernetes. There is, and I'm going to talk about this a little more, a runtime class that you can define to select which runtime you're going to use, and depending on the runtime you're going to use, you're going to add a different isolation layer. The hardware, the concept of virtual machine is now embedded into the OCI runtime specification. For those of you who know OCI, this is the canonical container runtime specification from the Open Container Initiative. And this, we added the definition of virtual machine into the specification. So the integration is seamless. This does already exist. You can already add a hardware virtualization and virtual machine as your container isolation layer. And the canonical implementation for doing this is Kata Containers. So what Kata Container really is about is implementing those addition to the spec, to the CRI specification, to the OCI specification, into a specific runtime, which is the Kata Container runtime. And the way, for example, you can use it is, this is a Kubernetes pod spec, a very, very simple one. It allows you to start a pod running one single container, a busybox container. It's probably very useless, but still. And the way you're gonna specify that you wanna run hardware virtualization as your main isolation layer is by specifying at the bottom there a new runtime class, a runtime class name, which is Kata runtime. And by doing this, you're telling your container infrastructure that for this specific pod, you're gonna use Kata runtime. And that means that you're gonna have hardware virtualization as your container, your isolation layer. Okay. So this looks very nice and very neat, very simple, right? It's beautiful, nice colors. You like the colors, right?
Yeah, I picked it.
Yeah. In reality, it's a lot more complex than it seems. And even the picture on the right is still a large simplification of the Kata container architecture. But in practice, your containers that compose your Kubernetes pod are all gonna run inside a virtual machine. It's actually a real virtual machine, so it's not like a trimmed down or hacked around virtual machine. It's a full-blown Linux virtual machine. So your containers that make your pod, and there's going to be one virtual machine per pod, by the way, but your containers that make your pod are going to run on top of a full Linux kernel inside a real full-blown virtual machine. They're going to be controlled by a specific agent inside the virtual machine, the Kata agent. Nice naming. And, well, the virtual machine is going to run on top of a VMM that's going to call into the KVM APIs. So which VMM are we talking about today? What does Kata use as the whole hypervisor stack or the VMM on top of KVM? We use, we support 3 different hypervisors, QEMU, NEMU, and Firecracker. So QEMU was the first one we supported. We relied on QEMU forever, and we're still relying on QEMU. It's the most performant, versatile, very stable, super reliable open source hypervisor out there. But that comes as a cost. It's very large. It's more than 1.5 million lines of code. And the footprint is also relatively large. So you get a lot of features from QEMU, a huge amount of features. It's a very complete hypervisor, or VMM, but the cost is that, well, your attack surface grows up and your footprint also grows up. On the other side of the spectrum, we support Firecracker. And Firecracker, she's a Firecracker maintainer. And Firecracker is very different from QEMU in the sense that its focus is very, very much, very much narrower than QEMU. So it's only built and designed for serverless containers, nothing else. As a consequence, the code base is much, much smaller than QEMU. And the footprint is also smaller, the potential attack surface is a lot smaller, and so on. The cost for this is that it is so narrow-minded on what kind of workload it's supposed to be running that it actually cannot run all container workloads. If you want to do things like assigning a device into your container, you want to assign your GPU or your FPGA or your SmartNIC inside your container, that's not something you're going to be able to do with Firecracker because, well, Amazon is running Firecracker in production in Lambda, and they don't do that. So they don't want this feature. They don't want to extend Firecracker to do that. If you want to have your container workload being elastic, being able to get more CPUs or get more memory, basically being able to hot plug stuff into your container workload, hot plug resources. Firecracker doesn't do that neither. If you want to share your host file system, you can't do that. So there's a few features that Firecracker does not support, and as a consequence, you can't run all workloads with Firecracker, right? So there's one elephant in the room. We're talking about Kata container, the new secure containers, making containers secure, blah, blah, blah. And We actually, by default, we're using QEMU. And on one hand, we're adding hardware virtualization to the container ecosystem. But on the other hand, we're adding a fairly large attack surface, a fairly large code base into this ecosystem. So we're claiming we're really secure. And on the other hand, we're kind of extending the attack surface from some perspective. And the other option is to use Firecracker. The attack surface is very small, but, well, you can't run all your workloads. So we thought about it, and we thought, well, we need something that really, really fits our needs, something that just clicks into exactly what we need for our container workloads. We need to work on something that only support the container workload, all container workloads, and nothing else. So the first thing we need to do to build that VMM that would only support our container workloads is to define what we need from this VMM. So we need to look at what defines a container. And the way to do this, there are many ways to do this, and you can look at many specifications. The natural way to look at this would be to look at the OCI runtime spec, but we took another approach and we said, well, we're going to look at the Kubernetes CRI interface, because eventually, typically, the CRI interface will call into the OCI interface in one way or another. So let's look at the higher level of all containers runtime specification, the Kubernetes CRI, and see what it means for a VMM to support the entire specification, the entire CRI interface. So let's look at it. So first of all, kubelet through the CRI is going to send some commands. And you're going to have to translate that into command that, for example, the Kata agent inside the container is going to be able to support. And for that able to do that, you need to have a concept of virtual socket so that the Kata agent can listen like an HTTP server, and the gRPC is going to do just that. So you can send gRPC command through your Kata agent that basically map what the CRI interface is asking for. If you look at, so on the left side here, it's basically fragment from the CRI spec itself. So we have the container config that tells you where the container workload is and all sort of things. And most of it means that we're going to need virtual storage. We're going to be able to have storage for volumes, also for the workload itself. We're going to be able to support virtual storage. Sounds reasonable, right? The CRI interface also specify your networking, somehow specify your networking configuration, and basically means you're going to need virtual networking. Then the three last ones are a little less obvious and more interesting. One thing that the CRI interface specifies is that you should be able to mount a device from your host into your container workload. So you should be able to, like I said, to mount your GPU inside your container workload. And that sounds very easy for a regular container where everything runs on the host. You have your dev GPU somewhere, and you can easily work around this and make it work. With a virtual machine and with a VMM, that basically means you need to do direct device assignment, VFIO, into your container workload. The mount structure basically means that you can mount something that's on the host file system into your container workload. Again, very easy when you run a regular container that runs directly on the host. When you need to mount an entire file system from the host into a virtual machine, not so easy. So you need a shared file system. You need your VMM to support the shared file system. And finally, the CRI interface tells us that there is a command to update the container resources. So you need to be able, hey, I want to have more CPUs, I want to have more memory, or I want to, have more resources into my container. And to do that, well, you need to hot plug stuff into your container, into your virtual machine. And when you're running on the host, well, the hardware is there. It's basically messing up with C groups, and you can work around this. When you're running with a virtual machine, you basically have to hot plug virtual CPUs, virtual memory, virtual NVDIMM into the container workload. So your VMM, the VMM that we want to build for container-specific workload, need to support resource hot plugging, all of them. So how does these requirements translate into actual technologies? The whole virtual socket, storage, and networking basically means that you're going to have, your VMM is going to have to support VirtIO, at least. vhost and vhost user, most likely, if you want to do some more fancy stuff and maybe more performance stuff. Device assignment, means that your VMM will have to support VFIO, which is a Linux-specific technology for basically assigning, having your user space VMM talking directly to your hardware, which is one way to assign a device into a virtual machine. The shell file system, the usual way to do this, and the way we're currently doing this with Kata Containers is 9PFS. Everyone loves 9PFS, maybe not so much, but the thing we're looking at right now is actually VirtIOFS, which is a new technology coming from Red Hat, which is about sharing a file system in a much more performant way than 9PFS. And finally, resource hot plugging means a lot of things, but you can do that through ACPI. You can use ACPI to do all your hot plug inside a platform. You can also do that through PCI native hot plugging. There are many ways. I'm not sure which one is the easiest, but ACPI is one way. So the requirements that we just built based on the CRI interface translate into these sets of technologies. And this is what our VMM, our container-specific VMM should at least have. So now we're going to look at where we could get all those features implemented, how we could manage to find the right components and put that together into the ideal VMM for containers.
So, sorry. The place where we can find all these components is actually rust-vmm. Rust-vmm, it's a new open source project that has as goal to provide building blocks for virtual machine monitors or hypervisors. These blocks are written in Rust, and each repository is basically one package, one component of the virtual machine monitor, and in Rust, these are called crates. So now let's look at why we decided to build rust-vmm. And to do that, I will just start with a story about Firecracker. Firecracker is a lightweight virtual machine monitor, and we started development in October 2017. And we started with the design phase, and we started looking at what programming language would be the best for a VMM, and we decided to use Rust. And after some weeks of development, we actually discovered there is another VMM written in Rust, which is CrossVM, and we decided to fork it and start our development from there. But Firecracker and CrossVM have very different use cases. So Firecracker is actually powering AWS Lambda, AWS Fargate, and these are, it is providing isolation for multi-tenant cloud workloads, while CrossVM is providing isolation for applications in Chromium OS. So they have very different use cases. And because they have different use cases, we almost instantly diverged. The project instantly diverged. But there are still a bunch of common virtualization components that could be shared. So the first idea with rust-vmm was actually to reduce code duplication between CrossVM and Firecracker. But in order for these virtualization components to be usable by both projects, we had to come up with a clean interface. So we are not just taking components and then putting them somewhere for both projects to use. We are also working on refactoring and providing a clean interface. And the good thing about clean interfaces is actually that it's much more easier to have security-focused and testable components. And one thing that is pretty interesting about this approach to have separate crates, packages, or repositories is that you can do security testing much more easier. So for example, fuzzing, because in a project like Firecracker, the only entry point is the RESTful API. But having components with clear interfaces allows you to do much more testing and get into a wider space of use cases. And then the last one, which is actually the most interesting point for this presentation, is the faster development for new custom VMMs. So having all these components here means that you can build new virtual machine monitors that are also very focused and targeting specific use cases, like, for example, a Container VMM. And you don't have to re-implement everything from scratch again, because you can use all the building blocks that already exist in rust-vmm to build your specific virtual machine monitor. So now let's look a bit at the rust-vmm development. So first, I want to start with big companies that are currently contributing to rust-vmm by providing feedback or writing code or anything. And one particular interesting group of people, which are usually not mentioned in presentations and whatsoever, are the individual contributors, and we do have some of them, and I really want to thank them. So let's see how we end up with crates in rust-vmm. There are two types of crates. So first, we have crates that are coming from either CrossVM or Firecracker. Examples here are wrappers over the KVM API, a minimal kernel loader, and so on. Then we have crates that are developed from scratch. So, for example, VirtioFS or ACPI or vhost user, which are very interesting for the container space. Now, everybody can contribute to rust-vmm, and we can look a bit in detail to the whole development process. People usually have ideas, and once they have an idea, they just open an issue in our GitHub community repository, and this issue has to have things like what is the proposed name for the crate, how is it going to be used, why is it useful for the rust-vmm community, and so on. And people provide feedback, and once we agree on a design, we create an empty crate. So that is the milestone 0. Then, based on the design that we agreed on, we start submitting pull requests. And basically, we now have a crate in development that has functionality, but it's not maybe very well tested, or it doesn't have documentation, and so on. And in order for us to move to the last milestone, so to speak, which means that the crate is actually published on Crates.io, there are a bunch of things that we have to do. So, Crates.io is actually a, how to say that? Is the crates, missing the word.
It's a repo.
Yeah, it's sort of
it's the official Rust repository.
Yeah, the official Rust repository, thank you.
Sure.
Okay, so now we have a useful crate, but there are a bunch of things that you have to do. So you have to have continuous integration, because these crates are going to be used by multiple projects. So you want to make sure that whatever you are providing to those projects is very well tested. So you add tested, you add continuous integration. And then you also have to add the license. And we agreed on having a MIT or Apache 2.0 as license. And one of the most important things, and people are ignoring it sometimes, is the documentation. And yeah, because we like to write code, right? But in Rust, you can actually write code in the documentation, and this is a quite nice thing, because people know how to use your public interface and knows what the function is supposed to do. So when you're updating a function, the tests will fail if your documentation is not updated. So those are the things that we have to have before publishing a crate to Crates.io. The current status, so as we have 3 milestones, I just put things like in 3 separate boxes. So empty crates, we have VMM vCPU, which is a hypervisor agnostic interface over interacting with vCPUs. Then we have a Linux loader, the VM Virtio, vhost, and VM device. So these are crates that might have PRs in flight, but they are not merged yet. Then we have a crate in development. This is VM memory, but we still have to work on adding some more tests and documentation and things like that. And then the only 2 crates that we currently have published on Crate.io are the KVM bindings and KVM IOCTLs. So now is the fun part where we are actually going to see how to build the VMM with rust-vmm. Only that, as I said earlier, we don't really have all the components published yet. So we are going to do a fake demo. Yeah. So we're going to start from the VMM API. So basically, this is the interaction point between our virtual machine and, for example, container runtime, Kata Containers.
Kata Containers, yes.
Yeah,
Kata
I don't know much
runtime.
about containers, sorry.
Those virtualization people, yeah.
Yeah, so we're starting from that. And then we can take a look at what is available on rust-vmm to start to decide what we need from there. And first, we are going to take the components that Samuel mentioned earlier, so ACPI, VirtIOFS, VM-VirtIO. But in order to have a functional virtual machine monitor, you need a bunch more things. So we will need to add the KVM IOCTLs, which essentially provides wrappers for creating a virtual machine, setting up memory for the virtual machine, configuring the number of vCPUs, and so on. Then we also need a kernel loader, which is responsible for loading the kernel image into guest memory. And since we are talking about guest memory, we also need something to provide an abstraction over interacting with guest memory, and that is VM memory. Now that we took all these components, the only thing that we still have to do is write the VMM glue. And by the VMM glue, I mean the code that is going to interact with all the components that we took from rust-vmm. That's about it. It should be simple. We'll see. So we are, what's next? So actually, we have a session at PTG tomorrow and Friday, where we are going to talk about what we want to do in the future and so on. But right now, we are thinking about adding hypervisor agnostic crates, and there are already some pull requests that are trying to do that. And specifically, we are adding Windows support and Hyper-V. Then, we are working on taking these components from rust-vmm and using them in already existing virtual machine monitors like Firecracker. And the last step, I would say, at least for this presentation, is to build this virtual machine monitor purpose-built for container workloads. But the truth is that we don't have everything figured out. So if you're interested or if you want to learn more, come talk to us and decide with us what is going to be the future of rust-vmm. So yeah, if you want to contribute to rust-vmm, you can attend our PTG session. You can become a member of rust-vmm on GitHub. You can subscribe to the rust-vmm email list. And if you want feedback, if you have an idea of a crate that would be useful for virtual machine monitors, you can submit a review request, and we are going to take a look at it and discuss on it.
OK, so as a conclusion, 3 points that we would like you guys to take back. First of all, VMs, they're now part of the container specification. So they are a standard container isolation layer. There is a need for a very container-specific VMM. There is no such thing right now. It's either too big or too small. And finally, rust-vmm is going to be our path forward into building this container-specific VMM by using the rust-vmm blocks and components and putting all them together. Well, not all of them, actually. Only the one that we need. And building this container-specific VMM. Thank you very much.